Today we're going to be doing some notes in nuclear chemistry. We're going to be talking about separating radioactive decays, penetrating power, and a little bit about accelerators. So let's start with separating radioactive decays. Since most radioactive decays are charged, then they can be separated very easily by putting them through a magnetic field. So here I would have a lead box, and here's a source of radiation. I have a little hole in the box so that way it shoots radiation in one direction only. And then here's two magnets. Now it should be pretty easy to understand this, that opposite charges attract. So if you look at the particles on table O, the negative ones would attract to the positive magnet, the positive ones would attract to the negative magnet, and the ones that have no charge wouldn't attract to either, and they would just keep going straight. So if we look at table O, and you should have this filled in, I didn't fill mine in, but you should have all of this part filled in from our previous notes, where it tells you exactly what these symbols are and what they mean and their charges and things like that. So you should have this filled in your notes, but the negative, the ones that are positive are going to go to the negative. So that means you're going to get alpha is going to go to the negative side, proton to the negative, and positron to the negative. And then the negative ones will go positive, so that's going to be beta, and that's it for the negative. And then the ones that have no charge are going to go straight through because they're not going to affect either one. So that's going to be a neutron because they're neutral, hence the name, and gammas because gammas have no charge either. And so that's how one way we can start to separate radioactive decays. Now let's talk about penetrating power. So penetrating power is basically how far the particle can bury into a solid object. Now, the reason we would care about this is if something is radioactive and you want to protect yourself from that radioactive source, you would really want to know how deep those particles can penetrate material, i.e. your body. Or the wall that you're building between you and the radioactive source so that you don't get irradiated. So penetrating power is kind of a important thing in certain scenarios. So it's actually based off of the mass of the particle. Turns out the biggest, heaviest particle is going to have the least penetrating power because it's big and heavy, and therefore it's not going to penetrate like a wall very easily, right? Like if you try to shoot a tennis ball through a concrete wall, because the tennis ball is so big, it's going to have a very hard time. If you try to do something like a really tiny bullet, even if it was moving at the same speed as the tennis ball, the bullet, because it's smaller, is going to have a better chance of penetrating. It doesn't really work well. That's a poor explanation because atoms are so outrageously small compared to both of those that it doesn't really matter. But that's pretty much how it works. So at the atomic level, it does work that way. So the particle with the lowest penetrating power would just be the heaviest particle on table O. So if you go to table O and you look that up, it's going to be alpha. And the reason is because alpha is 4. And so that's way heavier than the rest. So if you're being exposed to alpha radiation, then something like a piece of paper is all it takes to block alpha radiation. So your clothing can block alpha. Your skin, because the outer layer isn't alive, can block alpha. So we are it's very easy to block alpha as long as you don't ingest it or inhale it, because then it's very dangerous because you don't have a protective layer on your insides. The next one would be the next heaviest. And so the next heaviest would be beta. Now you could lump positron into here just as an exercise because positron technically is the same weight as a beta particle, but for other reasons positron isn't really going to penetrate much because of other things that I'm not going to get into. But they are the same weight, so we'll just lump them together. So yeah, beta particles can go through paper, they can penetrate your skin, but they may not go all the way through you, and a simple piece of wood, like if you have a wood door, that should be enough to stop beta particles from making it their way through. But if you're out and exposed, like in the sun, and there's a beta emitter, it could damage your skin and do things like that. Next, the ones that go through almost everything, and they are the lightest, is going to be gamma. Now, some people would say, well, wait, beta's 0 and gamma's 0, and so why aren't they the same? Now, the reason is because betas are electrons, and electrons do have some mass, although it's so small that when compared to the mass of a proton, we round it down to 0. But gamma is a form of light, right? And so gamma's mass is actually 0, whereas beta's mass is just so small we round it down to 0. Now that may not sound like a big difference, but being literally 0 and just being so tiny that you get rounded down comparatively is a huge difference in terms of mass. And so gamma has the highest penetrating power. So for gamma, it would be you would need a concrete wall, a relatively thick concrete wall, or lead to stop gamma, and even then, you will get a very small amount. I don't know if it's 1% or 0.1%, but you will get some gamma that may even still leak through a concrete wall, but it will be dramatically reduced. The concrete will stop most of the gamma from getting through. But some could potentially leak out. This is why when you go to a dentist office, right, and you get x-rays, the person, or if you go to the hospital and they think you have a broken bone and they x-ray you, they usually walk behind, they either leave the room or they walk behind like a half wall where they operate the machine. That wall, as well as all the other walls, is going to be filled with lead lined, or they're going to make it out of concrete depending on the building. And the reason is because the gamma rays, one, you get exposed every once in a while for an x-ray, right, or a cleaning at the dentist, but the dentist who's doing it, or the x-ray technician who's doing the x-rays, is doing hundreds in a day. They're potentially being exposed to more gamma rays in a single day than the average person gets in their entire life. And so they need to protect themselves. And so they go usually behind a wall, or they go behind, or they leave the room. And either way, the walls of that room would be made of concrete, or lead lined, or both. So that way the gamma doesn't go out. Because it's not just the gamma going through you. It's if you're, on one side of the wall and then there happens to be an office on the other side of the wall. If they don't make that wall concrete, then the gamma would go through you, through that wall, and then irradiate a person who isn't even aware of what's going on in the room next door. So the whole room is typically specially designed because it's going to have x-rays happen in it. So that's penetrating power. And then the last part is going to be accelerators. So in particle accelerators, what they do, there's a couple types. There's the circular ones, and then there's what's called a gun type, where they just shoot a particle like out of the barrel of a gun at another particle that's basically at the edge of the barrel, and then they smash the two together. But that's pretty much what accelerators do. They smash things together, and there is two goals. Either to find out what is inside of really small particles, like if you want to know what's in a proton, well, the best way to figure that out is to smash one open and look inside. And so that's not an easy thing to do, because two positive particles like protons don't want to come next to each other. So the only way you can really effectively break them open is smash them together at such high speeds that you can overcome the fact that the two positives don't want to be next to each other and break one or both of them open. And so that's what accelerators do. The other thing they do is they make bigger atoms. They try to take smaller atoms and make a big atom swallow a smaller atom by shooting it inside, and potentially make larger and larger atoms to see what kind of properties they may have. And so that's what accelerators do. They speed things up, they smash them together. Now the key is they use magnets to do this. So if you don't have charge, meaning these two right here, the neutron and the gamma, then you can't be accelerated in an accelerator, and therefore this isn't really good for you. So what they do is they've got these two big circles. Sometimes they're the same ring, sometimes they're different rings, depends on the design. And then they have an area where they have the detector, and that's where they cross the two paths, and then they hopefully, this is supposed to say bam, or whatever, explosion, right? They cross the two paths and they collide, and then they explode, or well, tiny little explosions, because we're talking about atoms, like a single atom. And then they view, using a special detector, what happened as a result. So that's how accelerators work. One thing I wanted to show you on the back is this is what an accelerator looks like in real life. This is the track. There's one track, and then you can see there's another track. Depending on the type of accelerator, one track could be like a pre-accelerator, and then the other one could be the real one. On the inside, it looks like this. This is the tube of magnets where the particles are going to be shooting through at nearly the speed of light. This is a scientist or someone on the maintenance team probably also a scientist, moving through. These things are so long that these tracks can literally be miles long. Some of the really big accelerators might even have room for an electric car underground so that you could drive through, because if this track is 15 miles long, you don't necessarily want to walk that loop several times a day, or even once for that matter. Notice this little building right here. Just to give you some perspective, that building, I believe that is the Fermi Lab. Google that when you get a chance. The Fermi Lab building is huge. This building is enormous. When you see people, if you Google it and you'll see people standing outside, you'll get a sense of how big it is. I don't know the exact height, but if I had to guess, I would say it's like 10, 15, 20 stories. It's a really big building. Not a skyscraper, but pretty large. And that'll give you some perspective on the size of these rings and just how large these facilities are in order to do this. And that is it for these notes.